atmosphere does have a huge effect on your ability to see things, and I can actually show you a pretty cool image of how that actually does it. And so let me pull that up really quick. And so if we switch over here and look at this picture, you notice that the sky is all real nice and kind of blue up here, but the closer you get to the horizon, you notice that it starts to get more and more red, and you actually start to see stars kind of start to disappear. So you can see tons of stars over here, tons of stars over there, but the closer you get down here, they kind of look like they kind of fade away. And this is the kind of stuff that you need to worry about, because if you're trying to view an object, if you're trying to find something here in the Milky Way and you're tracking it and tracking it, the closer you get to the horizon, the dimmer it's going to be, but also the more red. And so you kind of don't want that. So you got to figure out where exactly, is the best place to stop imaging. You don't want to image all the way to the horizon. And so there's a few things that affect that, and we can talk about those now. And so one of the things that astronomers and people talk about is the optical depth of the atmosphere, or the relative air mass. And so basically how they measure it is when you're looking up directly at the zenith, your relative air mass is 1. So you have basically 1 atmosphere to look through. And so that's going to be the most transparent view of objects in the sky. And so it's also going to be the best place to take pictures because you're looking through the least amount of atmosphere. And so just imagine, like, if you're in a pool, things that are, or in the ocean, if you've ever scuba dived, things that are closer always appear that they're, a little bit brighter, they're sharper, but the farther away that they get from you, things kind of start to disappear, especially in the ocean. There's only a certain distance at which you're able to see. And so that's the optical depth, and different types of materials have different optical depths. We even talk about optical depths of the sun and other stars and even planets and things like that. So basically it's just how far light can make it before it kind of disappears in that object. And so when we look back over here on that picture, you can see that the optical depth is causing kind of a disappearance of stars as it goes through there, because the atmosphere is absorbing them. But the reason why you're starting to see it more and more red down here is because our atmosphere actually allows more red light to penetrate through it than it does blue. It absorbs and scatters blue light more effectively than it does the red, and that's actually the reason why our skies are blue, is because of that scattering. So if you're tracking an object all the way up here and you're taking a blue image of it through a blue filter and you're getting it all the way down here, you're going to start losing more and more of that blue, and your image is going to be more and more red. So you're going to have to take that into consideration when you're actually doing stuff. So other things that you have to take into account for when you're doing looking up in the sky and things is the blurring effect that you get from the atmosphere. And this blurring effect in astronomy is called seeing. And so it's like, how well are you seeing things in the sky? This is basically caused by different densities of air due to different temperatures, and basically densities of the gases moving through the atmosphere. And if you're changing the densities of things, it's like having 2 different lenses of 2 different materials, and you're kind of moving them around like this, and you'll actually refract the light that's coming through them in slightly different directions, and that causes that light to be spread away from the actual source, and it causes it to be spread out. And that spreading out is kind of that blurring effect that you see. So if you're ever looking at like Jupiter or something and you see it really low on the horizon, you notice it's always like super fuzzy and it's hard to see any detail. But later on in the night, when it gets higher into the sky, you actually start to see more and more of that detail. And that's due to there's actually more atmosphere that you're looking through. It comes back to the optical depth of the sky. The more atmosphere you look through, the more of this blurring effect that is occurring, because you have more air moving stuff around that you actually have to go through. And so That's why it's best to be imaging and looking at stuff when it's as high in the sky as possible. Not saying that it's impossible to look at stuff really low on the horizon, but it's just never going to be as sharp as if it was high in the sky. And so there's really not anything that you can do about it unless you went to like the moon where there's no atmosphere, and then it's great. You don't have to worry about that. That's why we have the Hubble Space Telescope in space, is because we don't have this effect, and that's why people, astronomers and stuff, they have developed things like on the Keck telescopes, that basically use these little tiny mirrors and stuff to wiggle around and kind of bring all of that light that's being spread out by the atmosphere back into a single point, and that's adaptive optics. And they spent decades working on this kind of stuff to try to fix that, and they've been able to get to a point that their resolution is as good as the Hubble Space Telescope is, but it's only in certain wavelengths, because different wavelengths move and is scattered through the atmosphere and other materials that a little bit differently. And so it's not perfect, but it's a lot better than it used to be. I'm going to show you a video of what that actually looks like. So the video I'm going to show you is a video of Saturn. And so when you're looking at the image of Saturn, or this little movie of Saturn, you can actually see it waving in there. And that waving is that scattering of that light through the atmosphere. And you can actually kind of get an idea that the atmosphere is kind of what direction the atmosphere is moving and how it's moving just by how this is kind of wobbling. So it kind of looks like the atmosphere is moving from the right to the left, and you can see these little bits of the air density pockets moving across the image. So this is actually an image of Saturn that I tried to do at something like 30,000 millimeters on a telescope that we have. So we can look at the same kind of thing when you're looking at the moon, and you can kind of see how it's wobbling through there too. So you want to pick nights that are like actually really good and stable, and some locations are better at this than others. And you can see them kind of moving around, and you can see that there's a little bit of chromatic aberration there, that kind of reddish hue there. That is chromatic aberration due to the atmosphere itself sometimes. You can see it here. And so that is when the atmosphere is refracting light at different wavelengths differently. And sometimes it's an artifact of your optics. Some lower quality optics and even some medium quality optics will show this kind of stuff. But the atmosphere itself does that, and the lower and thicker atmosphere that you have, the more you're actually going to be seeing this. So to give you an idea of that the atmosphere does refract light, I'll show you this image right here. So the atmosphere does act like a lens to a certain point, and you can see that this image of the moon is no longer round. It's actually kind of squished down, and that's because the atmosphere is bending the light from below and kind of arcing it a little bit closer to this, and so you can see that it's no longer circular. And this is something really cool to look at through a telescope when you see the full moon rising on a really low horizon, and you can see this effect. It's actually really awesome. But you can see that the atmosphere does act like a lens, and that lens can cause like chromatic aberrations in images too. And so if you imagine you're trying to take a picture of like a galaxy or something and it's getting low on the horizon, you're actually looking through that, your galaxy is getting a lot fuzzier, but your galaxy is actually getting squished pretty similar to this, and so it's going to come out even worse than before. So it's not a good idea to take images when you get really close to the horizon unless this is the effect that you're going for. And so something else you can look at is there's other forms of seeing and stuff that can occur, and one of them is going to be at your optics. And so this is an unfocused star, and you can see basically the seeing that is inherent like around the mirror itself. You can see how this stuff is kind of moving around inside the mirror tube as the mirror and stuff is cooling off. You can create little eddy currents and stuff in there, and that's going to change your focus of the star too. And so you'll see it get brought into focus a little bit more, and then you'll still see a little bit of that wobbling around. But there are many different forms of seeing, and one of them is actually what's called local seeing or dome seeing, that come into effect just from like heat currents and things inside of your dome, or they could be inside of your telescope tube itself, like this was. So there was a mirror in there, is enclosed in a tube, and if you don't give it ample time for the mirror and everything to come to ambient temperatures, then you get these little heat movements and stuff in there like you saw in the video. And so that kind of gives you an idea of like some of the things you need to take into account later on. So you don't want to start imaging when your telescope is like 90 degrees and your outside temperature is like 60 degrees. You actually need to make sure that the temperatures come down to about the same, within a few degrees of each other. Otherwise you're going to be seeing this bad seeing, but you're also going to be changing the length of your optical tube because of thermal contraction, and then you have to refocus. And then if you don't refocus and you refocus at the higher temperatures, then later on you're going to notice that your stars are all, your objects and your stars are all going to be very blurry. So you got to take that into account. So another thing that affects your seeing and other aspects of your photography and your ability to see stuff is basically air turbulence. And so if you look at some pretty cool images online, you can actually look at areas above the ocean where there's islands and stuff, and you notice that the air down here is really nice, air over here is flowing really smoothly looking, but once you see the air move past, let's say, this island, you see all these turbulent air eddies that are coming through here, and that has a huge effect on a lot of different things. We can look at some other mountain peaks. So if you're in an area where there's a lot of mountain peaks like this, you have air flowing through here, you can kind of get an idea of where the best place to actually set up a telescope would be, and that's probably going to be on top of a mountain, because if you're looking through here, you see how much turbulence you get after the air flows past these areas. So the higher you are up here, the less of that turbulence you're actually going to be experiencing. And so you also want to be in an area where it's either really flat, where you can get this laminar flow. Laminar flow is basically flow that is not being disrupted over a long area. That way you're not seeing a bunch of effects. So there's other effects of this. You can see it like that. You can see what's happening right here. You see these things called gravity waves, which are not the same as gravitational waves, but you get this turbulence of air moving up and down, getting caught by gravity, then being pushed up by a compression wave. And you see this whole thing moving over here. So if you have a telescope out here, you're going to be seeing through all of this as it's moving past you. And this is the kind of thing that happens when you have a lot of mountains around. Also, you can see how much turbulence is coming through areas like this. So you want to be in an area where it's fairly flat, so you are seeing this turbulence, or you aren't seeing this turbulence. You don't want to be at the base of a mountain that has air flowing. You don't want to be on the back end of a mountain that has air coming over it. You would actually be better off being on the front of the mountain, where the air is actually moving past you and then to the mountain. You get a much better air through there. You can see it in this image also. And so it gives you an idea, like your local geography can have a big effect on what you're going to be seeing also. So if you're planning a night, or planning even to set up a whole observatory somewhere, you want to do it on a place that's actually good. This is the same problem that you would have with a lot of houses around. If you have a bunch of houses that are stacked on top of each other, you have wind coming through there, it's going to be a much more turbulent there, and that's going to be kind of a low turbulence instead of a higher up turbulence than you would have in an area where it's actually a lot wider open. But all of this actually comes to one point that you probably have noticed, even if you've never done astronomy, is like the twinkling of stars. And the twinkling of stars is actually caused by all of this. It's the blurring effect, that refraction in different, changing the paths of light as it's coming through our atmosphere, and it causes the twinkles. And since the atmosphere is kind of acting like a lens that bends light differently at different wavelengths, that's why you can kind of see some flashes of red or some blue on some of the brighter stars, because that light is being refracted a little bit differently in different angles, and so you're able to see little blips of color coming through there. A lot of people like to say that planets don't twinkle, but they do, just not as much, because stars are basically really, really far away. So they're basically a point source, and it's a lot easier to wiggle that point source around and cause that refraction of light in different ways. So it's a lot more noticeable. But your planet is going to be a lot larger because you can actually see it. It actually has a size to it, and so light coming from different areas isn't going to be as fracted, or it's not going to be as reflected or refracted in different ways quite as much, and so you won't be able to tell that it is being you won't be able to tell it's twinkling as much as if it was with a star. But if you're on a pretty turbulent night, you can actually look at a planet and you can actually see it twinkling fairly, kind of a lot. So that's something to check out too. And you can kind of get an idea of how turbulent your skies are by looking at how much the stars are twinkling in different areas, and that'll give you an idea of how sharp your images are going to be coming out later on.